Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to talk about a small signal condition for this amplifier and also the distortion, how we can calculate these formulas by hand, and in the end I'm gonna use LTspice to clarify our calculations. For small signal conditions, we're gonna look at the amplitude of this sinusoid applied to this circuit, and for the distortion we're going to use dot 4 for this analysis. But before we get started, if you're new here, please give me a thumbs up, hit that subscribe button and also notification bell, so whenever I upload a new video you'll be aware of it. Let's jump into it. So first of all, let's calculate a small signal condition for this circuit. What do I mean? I mean that how amplitude I can apply into the gate of this circuit so that I have a condition that the small signal conditions have been met, and I can follow with that to this circuit to get my result for example small signal, for example small signal gain of this amplifier. This is what I'm looking for. So here we go. Here this V out, I'm going to use this notation. This is V O in small signal. This is sorry, let me just this is some VO, this is large V, and this is a small o. Just consider this, okay? VO completely is included V capital O plus a small v small o. This means a large signal here. This is from large signal or a DC component of VO, and this one is a small signal of VO. For every signal, for example in VO or V in, we have two different components, so you had to take care of both of them. It is important. So here we have our total VO, and now I'm going to use KVL in this situation to calculate VO, and this is the ID through this R drain, and which is concluded from both the DC signal, the DC component, and the small signal. Okay, so here I have this V2 as a bias voltage, which is a fixed voltage, fixed DC voltage, minus RD times I drain. I drain is included from the complete DC and a small signal. Okay, you had to be careful about that. So here we go. VO equals to V2 minus RD times, instead of ID I'm going to use a saturation current through this circuit, because we set the VO in VODC into 0.9 volt, so the condition of saturation have been met. Weight drain source is greater than VGS minus V threshold. That's the case. So instead of ID, here we have mu n C oxide W over L divided by 2 times VGS. What is VGS? VGS is included, let me just have it, or I can just write V in here. Okay, here we go. Here we have V in minus V threshold voltage which is a fixed voltage of 0.4, all to the power of 2. This is ID. But here you had to be careful with Vin. Vin included both terms. Vin equals to capital V, capital In, which is a DC component, plus small v, small in. Now I'm going to substitute this formula into this one. Okay, so here we have VO equals to V2 minus RD mu n C oxide W over L, all divided by 2, times V in. And let me just a little bit organize this formula: minus V threshold plus V in, all to the power of 2. Now here this term is a DC term, which we can consider it as a DC current I drain that we all use it. Okay, now I'm going to expand this square formula in here. So VO equals to V2 minus 1 divided by 2 RD mu n C oxide W over L times V in minus V threshold plus a small v, small in to the power of 2. Now, in order to expand this formula, consider this one as a one term and this one as another. So here we can have it something like this. Here we have V in minus V threshold to the power of 2 plus V in to the power of 2 plus 2 times V in minus V threshold times V in. This is the expanded of this square formula in here. So here we have VO equals to V2 minus 1 divided by 2 RD mu n C oxide W over L. So now I'm going to just multiply this one by this so we have a great formula to follow our process. VO equals to V2 minus 1 divided by 2 RD mu n C oxide W over L times this term here, V in minus V threshold to the power of 2. Now about the other term here, this minus sign plus sign, minus 1 divided by 2 RD mu n C oxide W over L times Vn to the power of 2, and the last term here, 1 divided by 2 times 2 is 1, and here just we have this minus in here, so the last term would be minus, I don't have enough space in here, let me just write it down there, minus RD mu n C oxide W over L times V in minus V threshold times V in. So what is this term? This is a DC current term, sorry, the DC voltage of output voltage, And these are other results. This one in here is a nonlinear term. Why nonlinear? Because we have v into the power of 2. But here we have a linear term, which is a desired term that we're looking for, because we have v in output, and we have a just a constant coefficient into v in. So this term is a desired term that we're looking for, but this is unwanted. This is what we're looking. This is what we have, and we have to calculate the distortion from this term. Okay, but before that, let me just now calculate the small signal condition. What is the condition for a small signal? A small signal condition, it means that this nonlinear term had to be much less than desired term. This is how we can calculate the small signal condition. So easy. Okay, so here we have minus 1 divided by 2, and actually the amplitude of this term had to be less than this one. Okay, the amplitude of this nonlinear term. So get rid of these negative signs here. So 1 divided by 2 RD mu n C oxide W over L times V in squared had to be much less than this term here. RD mu n C oxide W over L times V in minus V threshold times V in. So it's so easy now, we can calculate it. These are the same terms that I'm gonna have to get rid of it, and one V in with V in is simplified, and so we have left with V in had to be much less than 2 times V in minus V threshold. And with our assumptions here, we can calculate V in had to be much less than 2 times this V in is 0.7, and this one here is 0.4. So here 0.3 times 2, 0.6. You had to choose the amplitude of V in much less than about 600 millivolt. Okay, and I choose 30 millivolt in my previous video for this amplifier. So this is a small signal condition, and this is how we can calculate it. Complete process. And now I'm going to look at the distortion, how we can come up with a formula for distortion, and after that we're going to check both of these formulas into our LTspice to clarify our results. Just look at the nonlinear term. This is a nonlinear term, as I told you, and let's just assume that we have a sinusoid into input and put it into this formula. So here we have our VO nonlinear. Let's call this. Okay, here we have this term mu n C oxide divided by 2 W over L RD V in squared, and we have V in as just the amplitude of V in times sinusoid as omega t, and we're gonna substitute this formula into this one. Okay, so here we have minus mu n C oxide divided by 2 W over L times RD. Now here we have V in to the power of 2 sinusoid squared omega t. Now I'm going to just simplify this formula by this one in here. If you all remember from your high school, sinusoid squared omega t, you can rewrite it as 1 minus cosine of 2 omega t divided by 2. I'm going to substitute this into this one. Okay, here we have minus mu n C oxide W over L times 2, but not 2 because we have another 2, so 2 times 2, which is 4 in here already, V in squared, and this one here we have 1 minus cosine of 2 omega t. Okay, now as you all can see, we have a term in the 2 omega. What is the coefficient of 2 omega? And this is the one, this is the case that we're going to define the VO distortion, the amplitude. What is the amplitude of VO distortion? The coefficient of cosine of 2 omega t. This minus and minus is going to be plus sign, so here we have mu n C oxide W over L divided by 4 RD times V in squared. This is the VO distortion amplitude. And what is the fundamental of VO? VO fundamental or VO desired. Okay, we already calculated. Here, this is the desired amplitude for VO. Now I'm going to use this formula here. Okay, here we have mu n C oxide W over L times V in minus V threshold times V in RD. Now we can calculate the distortion. What is the formula for distortion in here? The amplitude of VO distortion divided by the amplitude of VO fundamental. So here we have these ones. Mu n C oxide W over L divided by 4 RD Vn to the power of 2 divided by mu n C oxide W over L RD V in minus V threshold times V in. So here we can simplify this. These are all crossed out from dominator and denominator, and one of these V ins is simplified with this one. And remember that this is the amplitude of the sinusoid. So the final formula would be something like this: V in divided by 4 times V in minus V threshold. This is the last formula for distortion, and we can calculate it. So we can find the distortion of actually this is the normalized distortion of this amplifier. So what I choose for the amplitude, I choose 30 millivolt for the amplitude of my sinusoid divided by 4 times, what is the V in DC? It is 0.7 minus 0.4. If you calculate it, you can get the result that here we have 2.5 times 10 to the power of negative 2. And this is the result that I'm going to show you in the LTspice. So here we have it. Okay, this is the circuit that I'm showing you before. This is the sinusoid. This is the DC voltage of this sinusoid. This is the amplitude of the input signal. This is 1K as a frequency. This 2 means 2 cycles. This M1, the W would be 12.35 microamp, and L would be 1 microamp. And this is a model that I used, NCH. This is the model of this NMOS transistor, KP 180 microamp, and VT0 is going to be 0.54. The VDD would be 1.8. RD is 9 kilo ohm, and this is VO. This is the result for transition that I look for it in order to show you that this a small signal condition formula have been met. Let's just try this one. If I run this simulation, you can see the result for V in and VO, and this is really great output signal. If I get this higher, for example, instead of 30 milli, I use 300 milli. Remember the condition. The amplitude must be much less than 600 millivolt. If I hit enter and then rerun the simulation, as you can see, the output signal is not great. It's changing because the small signal condition have not been yet been met in this condition. So bear that in your mind. You have to be careful in your simulation. Okay. And about the Fourier analysis for calculating the distortion, I use this formula .4, and this 1K clarified the step conditions for the frequency and VVO. This is where we are looking for it, and you had to use these dot options. Plot bin size equals to 0 to disable the data compression normally performed for a transient simulation. This is from the book by Bruun in 2020, and this is neat in order to get accurate results for the distortion analysis. Okay, I'm going to put the references into the description. So here you had to run this simulation, and in order to find the result for distortion, you're just gonna have to hit Control L. It's that simple. Okay, Control L, and as you can see these are the steps of frequency, and in 2 kilo ohm you can see the result for normalized component 2.5 E minus 2. This is the result for from our calculations, and the total harmonic distortion would be 2.5%, most by this second harmonic. And as you can see, the next harmonic would be much less than, and it's almost 0. You see, e to the power of -9, e to the power of -8, and as you can see, these are just, you can simply neglect it, and most of the harmonic distortions comes from this second harmonic by the 2 omega t actually, which is 2 kilohertz. Okay. It is a really great idea to clarify your results with the simulation, but you had to, before that, you had to use some handy calculations. Maybe it's going to take a long journey for you, but it is really important to have both these skills for your design. You had to know some formulas behind it, and then clarify your result with the simulation. It is a really great way to learn through these methods as well. Okay guys, I hope you like this video. If that's the case, please give me a thumbs up, share this video with your friends, and see you in the next video. Thanks for watching.